Hello everyone and welcome to 142 Lab. My name is Oliver and I'll be your TA for this strange quarter. Each week I'm going to provide a video that will walk through the lab handout for that week's lab. You should follow along with the lab handout slides and please email me if you have any questions. Okay, let's get started with the first lab. We'll begin with making polynomials in the frequency domain. As a refresher, control systems often use the frequency domain with the variable s instead of the time domain, so s will have units of radians per second. To construct a polynomial, we'll make an array of polynomial coefficients. This is done here with p. So p can be said to equal to s cubed plus 3s squared plus 0s plus 4. If we want to find the roots of the polynomial, we can simply use the roots function, which will provide an array of the roots. And if we want to reconstruct the polynomial using the roots, we can do that with the poly function. Okay, so to multiply two polynomials together, we'll do the following. First, we'll make the two polynomials that we want to multiply, here with p and q, and then we'll use the con function to multiply the polynomials together. So with this n polynomial, which is the product of p and q polynomials, we can use the polyval function to, say, evaluate the polynomial n for a value of -5. So if we run this code, we can see, okay, here's the array of coefficients for p. Here are the roots using the roots function. We can reconstruct the polynomial using a poly function, and then if we multiply the two polynomials together, we get the n polynomial, and it's given here in terms of the coefficients. And if we evaluate at -5, we get -66. Okay, let's move on to transfer functions. To make a transfer function, we'll make the polynomial of the numerator and a polynomial for the denominator, and then we'll put them together using the TF function. So here we have the numerator is 10, where the denominator is s squared plus 2s plus 5, and we put the systems together using the TF function, where the numerator comes first as an input and then the denominator. In our second transfer function, we'll have a numerator of 1 and a denominator of s plus 1, or 1s plus 1, and then we'll put them together using the TF function. So now I have system 1 and system 2, and then we can add the two transfer functions together just by using the addition key. So let's talk about poles and zeros. So as a refresher, poles are the roots of the denominator of a transfer function. In other words, they are the values for s that make the function blow up to infinity. And zeros are the roots for the numerator of the transfer function, and they're the values of s that make the function equal to 0. So first, we'll make a transfer function called sys, or system, with the following numerator and denominators, and then we'll find the poles of the transfer function using the pole function, and then we'll find the zeros using the zero function, and you can do this respectively for poles and zeros, and then you'll store them in arrays called p and z. But if you want to do this on one line of code, you can just use pzmap, and you'll store these poles and zeros into p and z. So if we run this code, we'll see that lowercase p and z are -1, -1, and -10. So that's these two lines here. But if we use pzmap, we get the same thing for uppercase p and uppercase z. Okay, so let's go to an example problem. First, we'll make g of s, which is simply the transfer function with the following numerator and denominator. And then we'll also find the poles of g of s here. And then making h of s will require a few more steps, since it's created by 2 numerators and 3 denominators. So we'll have the 2 numerators here, and then we'll give the denominators here. Note that the denominators are complex, so MATLAB can do complex, can account for the complex numbers. So the numerators will just multiply together using conv, and the denominators will do the same thing, but with 2 functions of conv. So first for denominator 2 and 3, and then we'll conv together that product with d1. And then our h of s is going to be the numerator that we solve for here and the denominator that we solve for here. And then if we want to do a division, say g of s divided by h of s, we have g of s divided by h of s. So you just use the division key. And we'll put that into, we'll set that equal to a new transfer function called sys, and then we'll do a PZ map of sys. So instead of storing the poles and zeros into arrays like we did here, we're just going to plot it. So let's see what we get. So here's our PZ map, and you can see we have the poles and zeros. Moving on to block diagrams. First, we'll make a transfer function for g, and then a transfer function for h. And we'll say that if the transfer function g of s and h of s are in series, and we want to make a system that represents that series, then we can use the series function, and that will combine the two transfer functions as if they're in series into one transfer function. And we can do the same thing if they're parallel. If you're having trouble visualizing series and parallel, just think about it like resistors. All right, moving on to feedback. So if g of s has negative unity feedback, then we'll use the feedback function. The first input is a transfer function receiving the feedback, so that will be g of s. And then the second input is the sign of the feedback. So -1 means that we're going to have negative feedback. So we're subtracting the feedback from the system. If g of s has negative feedback with h of s, so not unity, it means that the feedback has a transfer function in the path, then we have the g of s, which is the system receiving the feedback. We have h of s, which is in the feedback. Before we didn't have a function in the feedback, now we do. And -1 says we're subtracting the feedback. So let's do a block diagram example. First, we'll make the transfer functions for g of s and c of s. We'll call them system1 and system2. And then let's say they're in series, and you should follow in the slides and you'll get pictures of these. So they're in series, so we'll combine them as so using the series function. And then we'll have positive unity feedback. So we use the feedback with a sign of 1. Again, the unity feedback means that there is no transfer function in the feedback path, and the positive aspect means that we're adding the feedback to the system. Okay, lastly, if instead we have system1 with a feedback of system2, we can use the feedback function in this way. And if we don't specify the sign of the feedback, MATLAB assumes that it will be negative feedback. So that's, if we have -1 here, then it's the same as having nothing. Okay, moving on to the min-real function. The min-real function reduces a transfer function's coefficient and attempts to cancel terms if possible. So here we'll make system1 and system2. Here's system1. Sorry, we're just making system1, which has, pretty large numbers in the denominator, right, and then the numerator. And so we use the min-real to reduce these coefficients, and that'll produce the following. So here we have the first transfer function, which has large numbers, right, and then we have our min-real version, which has much reduced numbers. See, the leading coefficient here is 1, and up above it was 12. So divide everything by 12. Okay, so now let's move on to the step response. So we'll provide a transfer function with a step input. If you remember from vibrations, a step input is simply a constant input that is applied to a system indefinitely at a given period of after a given period of time. Most of the times it's applied instantly. So first we'll make an array for time here, which starts from 0 seconds and goes to 100 seconds in increments of 0.01 seconds. And then we will make the arrays for displacement and time for the transfer function system that undergoes a step response. So we've described what time is. We use the previous system from the min-row function, and then we can plot, we can make the arrays for the displacement, if you will, for y and the time. And then using these two arrays, we can plot, and we get the following response here. Okay, so that's all for this week. Please let me know if you have any questions, and keep an eye on the announcements section in Camino because I'll be posting answers to common questions there.